Have you ever stopped to think about what's actually going on when you twist a rope or wring out a wet towel? I mean, really think about it. Well, there's this hidden world of physics happening in that simple motion. And today we're going to dive deep and unpack the science of the twist.
And really, it all boils down to this one question. Why is it that some materials, like a thick steel cable, can handle a ton of twisting force, but something like an old rope just frays and snaps? Look, understanding this isn't just for engineers. It's the science that explains pretty much everything, from how durable your shoelaces are to the strength of the clothes you're wearing right now.
So here's how we're going to unravel this whole thing. First, we'll get into the basic science of what twisting even is. Then we'll explore how materials fight back against that twist. After that, we'll see how different fibers actually stack up when you put them under pressure. And finally, we'll find out what happens when they hit their absolute breaking point.
All right, first up, the basic science. Let's imagine we have a super-powered microscope and zoom all the way in to see what's really going on when a material gets hit with a twisting force, or as physicists like to call it, torque. The official name for all this is torsional properties. It sounds complicated, but it's really just a simple way of describing how any material behaves when you twist it. Think of it as the rulebook for rotation and resistance. Now, to really get this, we're going to focus on two main ideas. First, you've got torsional rigidity. That's basically how much a material fights back when you try to twist it. And second, there's the breaking twist, which is pretty much what it sounds like, the absolute limit before it just gives up and fails. So let's start with rigidity.
Okay, so let's dig into our first big concept, torsional rigidity. You can kind of think of this as a material's stubbornness, you know? It's that built-in quality that makes it tough to twist in the first place.
Okay, let's get just a little bit technical here. The scientific definition of torsional rigidity is the amount of torque, or twisting force, you need to apply to twist a 1 meter long piece by 1 unit of angle. To put it simply, the bigger the number, the tougher it is to twist. That's it.
Now check this out, because this visual makes it so clear. Imagine you draw a perfectly straight line from A to B down the side of a cylinder. When you twist that cylinder, that straight line gets warped and stretched into a new position, A to B prime. That distortion has a name. It's called shear, and that idea is right at the heart of torsion. And here's what's really fascinating, that force isn't felt equally across the whole thing. Not at all. If you look at a slice of it, the very center of the cylinder hardly even moves. The shear there is basically zero, but as you move toward the outer edge, the stress and that distortion get bigger and bigger until it's at its absolute maximum right on the surface.
Okay, I know what you're thinking, a formula, but don't let it scare you. It's better to think of it like a recipe for resistance. All it's telling us is that a material's rigidity depends on a few key ingredients: its shape, its internal stiffness, and how dense it is. You change any one of those, and you totally change how much the material fights back when you twist it.
So that's the theory. But how does all this actually play out in the real world with stuff we use every single day? Let's put a couple of common fibers to the test.
All right, pop quiz time. Let's take two materials you are probably wearing right now, cotton and polyester. One's natural, the other is synthetic. Just based on what you know, which one do you think has a higher torsional rigidity? Which one is more resistant to twisting? Go on, take a guess.
And the answer, which might actually surprise you, is cotton. And it's not even close. If you look at the data, you can see that natural fibers like cotton and wool are way more resistant to twisting than synthetics like polyester and nylon. Why? Well, it mostly comes down to their complex, naturally grown molecular structures, which just create a lot more internal friction. Pretty cool, huh?
But look, being rigid is only half the story. Every single material, no matter how stubborn it is, has a limit. So for this last part, let's talk about that absolute limit, the breaking point. How much twist is just too much?
So the way scientists measure this is with something called the breaking twist angle, or BTA. This is the exact angle of that shear, that distortion we saw in the diagram earlier, at the very split second that the fiber fails. It's the material's final word, no going back from there.
So how do we figure out that exact angle? Let's just walk through a really quick calculation together. The formula is actually pretty simple. It just uses the fiber's diameter and its breaking twist value. So, using some data from our source, for a specific fiber, it has a diameter of 0.1 millimeters and a breaking twist of 40 twists per inch. We just plug in the numbers. And what do we get? This fiber's breaking twist angle is precisely 26.32 degrees. Any more twist than that, and snap, it's gone.
And that pretty much wraps it up. We've gone from a simple, everyday motion
all the way to the complex physics that governs the strength of materials. The big takeaway here is that this hidden science isn't just happening in some lab. It is literally woven into the fabric of our world. It's in the ropes we trust, the bridges we cross, and yep, even the clothes we wear. Which leaves me with one last question for you. Next time you pick out a shirt, are you going to think about the twist?